Welcome back, friends. Today we'll be assembling the low-cost keyboard by Don Lancaster that was featured in Radio Electronics February 1973 issue. Don Lancaster, who unfortunately passed away a few years ago, designed many circuits and projects for hobbyists throughout his life, and actually kept on responding to emails from hobbyists until his death. One of his notable projects was the TV typewriter, and the TV typewriter actually used one of these keyboards for data entry. In a future video, we'll be building the TV typewriter as well, and it will require an ASCII keyboard. In that article, Don recommended using the low-cost keyboard for the TV typewriter or one of the surplus keyboards. I've decided to use the low-cost keyboard in my case. The goal in this video is to reproduce the keyboard that he designed in that article. If you try searching online for PCBs for this keyboard, there's a high chance that you won't find anything because they're not available. So purchasing a PCB is not an option. I knew that I wanted to build this keyboard, and seeing how there were no existing PCBs or fabrication files available online anywhere, I've decided to make them myself. I took the artwork from that article, and after many hours was able to produce Gerber files for both the keyboard itself that was featured in that article and the ASCII encoder that Don designed as well. But it was featured in the I think it was the April issue of the Radio Electronics magazine a few months later. We'll be assembling both of these PCBs in this video. The article for this keyboard describes in detail on building the key stems and keycaps for this keyboard. The PCBs that I made actually assumes that these key stems are used. This process is actually very difficult for most people. Because of that, I actually made another variant of this PCB that actually accepts modern MX switches. So, for example, here's the original design of the PCB, which accepts the key stems that were described in the article. And here's the modern key switch variant, which basically all it requires are just a bunch of modern MX key switches and a couple of jumper wires. I'll have both the modern variant and also the original variant available at callencheck.com for anyone interested in building the keyboard from scratch. As I mentioned earlier, the encoder for the low-cost keyboard was introduced 2 months later in the April issue of the Radio Electronics magazine. And this encoder was specifically designed for the low-cost keyboard, but it could potentially be used for other keyboards as well, since it's just a layout of keys. That's all it is. This encoder was termed the brute force encoder since it used basic components to implement the logic for converting the binary signals into ASCII code. Mr. Lancaster later went on to build the improved ASCII encoder, which was a much better version than the original encoder. But since the project that we'll be using the keyboard with uses the first version, we'll also build the first version. And this is what it will actually look like. I'll have these for sale at www.callencheck.com along with the keyboard PCBs. All the parts in the articles are fairly easy to source. I'll include details about specific parts in a GitHub repo that I'll link to in the description, such as where to find the hard-to-find components. The keycaps I found on Amazon, it was basically a big set of keys that I could pick and choose from, but unfortunately not all keys were there, so we'll just use placeholders for the time being until I can either find them or build them myself. Alright, let's start the assembly on the keyboard, and once we finish that and test it, we'll move on to the encoder. As I mentioned, I'll be assembling the modern variant of the PCB, which accepts the modern MX switches, instead of the one with the key stems that we have to make manually, which, by the way, I'll still build eventually in a future video. The only thing that we have to solder on this board are the modern MX switches, and also some of the jumper wires. I went ahead and populated the PCB with all of the MX key switches, and also the keycaps that I got on Amazon. This is obviously not the finalized version of key switches, but we'll just basically use them as placeholders for the time being. So what I'm going to do now is tape this down so it doesn't fall out and try to solder it in. Alright, so we got the keys soldered in, key switches. The spacebar here is not finished yet. We still have to do something about these, I forget what they're called. Basically, I guess they're called stabilizers. Probably need to glue them in or screw them in or something. We'll do that later. And also the shift key as well. But for now, what we're going to do is solder in, basically finish soldering. And the only thing that's left to solder are these here, basically all these jumper wires. And the way that we're going to solder them are basically like this. The bottom set of holes that go on top of the keys here and continues here on the side, all those holes have a corresponding hole right above it. So whenever we jumper a bottom hole, we have to jumper it to the hole right above that. So we need jumpers for all of these holes, and there should be about 104 of them. Okay, we're finished with that part. This took a while just to trim each jumper wire and insert it into its positions here. I still have to solder it in, but the time-consuming part is finished, fortunately. So I'm going to go ahead and add some tape to this and solder it in. So all the jumpers have been soldered in. I think it looks pretty good. This keyboard sounds pretty good and pretty nice to type on. You know, it's almost ready. There's one thing that I still need to do, actually two things, but I'll do this later. So the first one is this shift key. I need to install a stabilizer here so that when I press on the key, that it actually presses down evenly, just similar to how this space bar works. And so with this space bar, the PCB has three footprints for, I guess, three separate key switches that we could have installed, but I just installed a single one for the space bar, and then I added this stabilizer bar here so that when I press anywhere on the key, the whole key goes down at the same time. Obviously it's not going to work yet because I still need to do one thing, and that is to attach these attach the stabilizer bar to the PCB somehow. So for example, if I hold it down here and I press it down, it goes down together as the whole key. So what I have to do now is figure out a way to attach this to the PCB, and I'm thinking I'm gonna basically epoxy these two white plastic pieces to the PCB itself. Okay, so I applied some, actually I used Gorilla Glue instead of epoxy. I just applied it here. It's not fully cured yet, but I think it looks pretty good already. So we can For example, press the space bar in any location and it goes down evenly. I think it looks pretty good. So what I want to do right now is basically do a quick test to make sure that, like, if I press a key, that the correct pinouts here are shorted. We can use this article here for the ASCII encoder in the Radio Electronics magazine April 1973 issue, because if we look at the pinouts here for the connector on the encoder, basically this side of it, of the encoder, is the input side, and it's coming from the keyboard. And we can see which keys are actually part of which pin on the encoder here. The easier way is to basically look at the PCB itself and see which one is supposed to short when we press a key. So for example, the delete key, the last one on the right, or the top right, we can see that the first pin here and the second to the last pin here should be shorted when the delete key is pressed. And we can test the other ones the same way. So let's see if that's actually the case. Let's try to press the delete key and see if it's going to short those two pins. So the first pin and the second to the left pin, from starting counting from the bottom, it's not shorted now, but what if we press the key? All right, so it appears to be working. We can test the other keys the same way. I'm going to let this epoxy here dry before doing anything else with the keyboard here. And in the meantime, we're going to assemble the ASCII encoder for the keyboard. And here we have the ASCII encoder board that the artwork itself I got from the Radio Electronics magazine article. So this is on page 59. Actually, it goes something like this. Obviously, it's not going to 100% match up because it's not to scale. One way to transfer this image to PCB is to use toner transfer, and that's what a lot of people did back in the day, but I ended up doing it digitally. I converted this to digital format. I sized it. I cleaned it up. It took a while actually to clean it up and make it neat and aligned. And then got the PCB fabricated. So this article actually starts on page 55 here, and we can see that this is by Don Lancaster. And the subtitle says that here is where you need to couple the keyboard you built in February, which is the keyboard that we just assembled, to a computer, teletype, or teaching machine. So this encoder was specifically designed for the keyboard that we just assembled. On the next page, we have the parts list, which are all the parts that we have here. There aren't that many parts, so it shouldn't take too long to assemble it. And the schematic. And then on the next page, we have the artwork for the PCB traces and the parts layout. Unfortunately, I couldn't get the silkscreen to align with all the parts on the PCB, and actually I used a different image that I found online for the silkscreen, and it just wasn't good quality, so I couldn't get it to work. But I think that the one that we have here in the physical article is a little better quality. I might modify the Gerber file to include the silkscreen, so that we can actually have the silkscreen on this board here in future sets of these boards. But for now, since we don't have the silkscreen outlined on the PCB, we're going to have to go off of this image here to know where each part goes. So let's go ahead and start the assembly, and we're going to start the assembly with the resistors as usual. And I'm just going to keep this article to my side here just so I could go off of it to know where each component goes. And we can reference the parts list on this other page, page 56. So R1, resistor 1 is 390 ohm, and it's actually right here. So let's go ahead and install that. Okay, we got all the resistors installed. After installing all the resistors, I realized that it might help to go through the layout or the silkscreen image and just mark all the components on the PCB, and it will make it much easier to install the components later. Next, we'll install the diodes, and if we look at the parts list here, the parts list calls for two different types of diodes. There's one 1N4736 diode, which is a Zener diode, D27, and the rest of the diodes are 1N914. So let's install the D27 diode first, and then the rest will be just one type of diode. We got the diodes soldered in. There's one mistake on the parts placement that I want to mention. So if we look at the parts placement, D13 right here, it's showing that it should be connected between the HO and the ZXZ pinouts here on the PCB. And that's actually a mistake. Whoever printed this page actually made a mistake on the placement of D13. This symbol and the text for it should be actually right here, right between D25 and D15, I think. And there's actually pads for it here. So I think when I made this PCB, I think I accounted for that. So the pads do exist for D13 right here, which goes here, and I didn't include the pads for D13 here because that looked wrong. It didn't even have pads for it on this side. So that should be the right placement for D13 right here. Additionally, I had to remove this resistor here, R6, because I had installed it into the wrong hole here. So I removed it and installed another one here so that I can install a diode in the correct hole. Okay, next thing we're going to install are the jumpers. So there's a couple of jumpers throughout the PCB. And since we're still working on the low profile components, we might as well install the jumpers. All right. Next, we'll install the IC sockets, and there's 3 of them. And I got some interesting ones. I think these are from the 1970s, if I'm not mistaken. And supposedly they are not as, I guess, not as reliable. Basically, they don't make a good contact. So we'll see how they work. If they're not very good, I might just remove them and install better ones. But I like that they look kind of retro from that time period as this encoder. So let's go ahead and install them. And all of them face up, so basically pin 1 needs to face up. Next, we'll install the transistors. There's 2 different kinds of transistors. A PNP transistor, there's actually 4 of them, 2N5139, and NPN transistors, 2N5129. And there's actually 8 of them total. I think the way they're supposed to be oriented is like this. So basically, if you take a look at the pins here, we can see sort of a triangle here. We want to have the base pin, the middle pin, be in the basically where the arrow points to. Basically, that's going to be where the base will be, and the transistor is oriented in that way as well. So just follow the way the transistor is oriented with the way the footprint is oriented, and just make sure that you're installing the correct transistor in the correct footprint. And finally, we can install the capacitors. There's one ceramic capacitor, which is C1. If we look at the diagram here, we can see that C1 is actually right here. So we'll install a ceramic capacitor into that. That's a 0.1 microfarads. And 2 electrolytic capacitors, C2 and C3, 100 microfarads, 10 volts. And we just want to make sure that we orient them correctly with the plus sign going down. Okay, so all the solderable components have been installed. The next thing we want to do is install the integrated circuits, and there are 3 MC9818 ICs that need to be installed in here. I think I got these on eBay, if I'm not mistaken. They're fairly available, but they are not as common as some other integrated circuits. Okay, and they're in. I think these are inverters, if I'm not mistaken. Let's take a look at the schematic here. Let's take a look at the schematic. So they are inverters. These are hex inverters, basically. There's 6 of them in one integrated circuit. Okay, the PCB is finished. What we want to do now is test it out. So what I will do is, so one way to test it is to basically manually apply some sort of data on the inputs here, and then read the outputs to see if they're correct based on the selection. Basically right here, so we have the inputs and then we have the outputs. But since we already have the keyboard ready and built, we can basically hook it up in here and apply power to this board through the connectors here. Basically, I think it's pin 1 is ground, and the last pin is, so it's actually not pin 1. So pin 12 is ground and pin 1 is positive. I I think this PCB calls for positive 10 volts. I think, if I'm not mistaken, the project that we'll be working on actually will have positive 12 volts. So I'm going to see if I can actually apply 12 volts into here and see if it's going to work. I'm going to go ahead and wash this board, let it dry, and then hook it up to the keyboard. So the way we would attach the encoder to the keyboard is basically attaching it directly to the output here. So this side goes into here, and we have to actually orient it like this, so that this pin here attaches to this pin here. Instead of doing it like this, we have to do it like this. Because if we look at the article here, we can see that the delete key is here, and the delete key on the keyboard itself is here as well. So we want to make sure that we actually align it correctly. And the way we're going to attach it is by using these connectors here, and these should just go in, like insert like this into the encoder. If it doesn't insert, if it's too big, for example, you can probably just shave off a little bit of these sides. And also on the keyboard, that should do the same thing, just like that. So what we're going to do, or I guess what we could do, is basically run some wires directly to here, to each of these pins. But I won't run all the wires directly. The reason why is because if we look at the article for the low-cost keyboard here on page 54, this key mechanism is using foam that's conductive, and that foam has some resistance. So the circuit is made to work with some resistance. And if we look down here on the page, it's actually says here that it has to be under 500 ohms of resistance. So if we add some resistors to on each line that goes from the keyboard to the encoder, we can prevent the circuit from breaking unintentionally. So, for example, we could apply resistors on this line here, on these lines here, or these bottom ones, the 000 to 111. I think I'm going to apply it to the bottom ones, and the reason why is because there's less of them. But yeah, I'm going to add probably like a 330 ohm resistor on all of the 000 to 111 lines. Okay, so I got this cable soldered and ready to go. I'm gonna clean it up and make it a little bit nicer later, but for now I'm just gonna use it for testing. So I'll plug one end of it to the encoder with the resistor side down. And the other end will connect to the keyboard. We're gonna have to have the encoder be upside down because that's how it connects to the keyboard. just like that. And now we just have to supply power and test it out and see if we can actually get an ASCII code output on the encoder. I've got the encoder hooked up to an oscilloscope and also applied 10 volts of power to the encoder. So now let's see if we can actually produce some kind of output by pressing the keys on the keyboard. We can watch the oscilloscope as we press a key. So for example, I got the oscilloscope hooked up to, one probe is hooked up to the keyboard pressed key. So whenever a key is pressed, it will, I guess, fall down too low. It's normally high, and then when a key is pressed, it falls too low. And the other probe I got hooked up to bit 5. So, for example, if I press the A key right now, we can see that the blue line is the key pressed signal. So it fell too low whenever I pressed the key. And the yellow line is the actual value for bit 5 of the key that I pressed. So in this case, it was A. So if we look at the ASCII table here, so for example, we're looking at the letter A, we want to see what bit 5 is here. So for A, it's actually 0, and that's exactly what we're seeing on the oscilloscope there. What if we press, let's say, R, which should give us a 1, a high signal. So I'm going to go ahead and press an R. Actually, I'm going to reset the oscilloscope first. Okay, now we can press an R. So as before, we see the blue line drop down to 0, which means a key was pressed. But this time the yellow line actually went up to high because the ASCII code table here for R was showing bit 5 as high. So it appears to be working correctly, at least for bit 5. That's the only bit that I tried. We can probably test the other bits as well, but my assumption is that it's actually working properly. And I'm actually going to go ahead and test it offline here just to make sure that it's working properly. I connected the encoder to another power supply that I had, which was a variable voltage power supply. And I set the voltage to 12 volts, and the waveform on the oscilloscope became much cleaner and nicer. So now whenever I press a key on the keyboard, the wave is just solid. It doesn't do that wavy up and down kind of thing that we saw earlier when I was using the other power supply. So yeah, I'm much more satisfied with this wave than I did with the other one. So I think either this power supply is much better than the one that I was using previously, or the fact that I'm using positive 12 volts here instead of 10 volts is making a big difference. Once I was satisfied with the waveform seen on the oscilloscope, I made a little circuit on a breadboard to be able to see all the bits for the key presses. And this circuit is pretty basic, but all it was intended to do was to basically latch the entire ASCII code in a SR latch, I think, and then output it on LEDs. And unfortunately, it didn't work as expected. It wouldn't stay latched, but that's fine because I was able to basically demonstrate that the data coming from the keyboard, the ASCII code that's coming from the keyboard, is actually the correct code. So for example, if we press the letter A on the keyboard, we should be able to see the ASCII code 1000001. And we can go down the list pressing the C and getting the correct ASCII code for that, and then D, and it's also correct, E, and then F and G, H, and just go down the alphabet, selecting all the keys in order, and we can verify that the ASCII code is actually correct for all keys. So This circuit is actually pretty nice because we can demonstrate any character on the keyboard directly on the LEDs to see which ASCII code is being displayed. Friends, that will be it for this video. We built Don Lancaster's low-cost keyboard and its accompanying ASCII encoder. We can now use this keyboard for practically any retro computer to input data into the computer, but my goal is to use this keyboard for the TV typewriter, which is a project that is coming up soon. So if you haven't subscribed yet, now is your chance. Thank you for watching this video. I hope you enjoyed it, and I'll see you in the next one.